Okay, so we got going. Hello. Oh, I was supposed to start this. Okay. So welcome to the pre-live stream. Today we're gonna walk through some how can we use HLS to do rapid prototyping of some video filters. We're going to do custom HLS video filters today, and next week we'll look at trying to integrate Xilinx's OpenCV HLS library. I looked at it before, I've never integrated it before, so that'll be interesting. So welcome to our stream. Any recap to any new viewers? We're using Xilinx's Artix UltraScale Plus FPGA on Opal Kelly's dev board, the XEM8320. It has a bunch of SYZYGY ports. Today we'll be using the camera one on their standard port. It's been working great so far. Easy to set up with their example design and get working. So today we're going to poke at it a little more and see what we can do with it. So first, let's get some news out of the way. If you're, watching this, feel free to like and subscribe to the channel. It helps us get the videos out a little bit better. Next, let's see, and Twitch. So next month, I'm going to try doing YouTube and Twitch streaming to see how that works. Also, I'll try to do a Discord server at 1,000 subscribers. And after we get that going, we'll try to see what other goals we can do. But feel free to kind of, I guess, join my community. It seems weird to say, but take part and support what you see worth supporting. So today, I got the camera working at 60 frames per second. So we're going to talk about those settings that I did. And then we're going to try to see how much HLS we can get through. Might have to split this up into 2 sessions. We'll see how much we can get done. An hour and a half, but we'll try our best. So let's get going so we can get as much done as possible. So first, let's talk about 60 frames per second. So before, we were able to do this PLL setting on the clock to increase the clock speed. So I kind of have 4 different things I had to do to get the clock at 60 frames per second. The first thing, I set this to 64, which seems to be the highest reliable image. Then in Vivado, not this Vivado, the other Vivado. Where's the other Vivado? Apparently I don't have the other Vivado up right now. So we'll open it because that's the one we're going to be using. No. So looking at the documentation for, is it like 196? 96. Right here, the pixel rate clock is 196. That's the fastest clock that the pixel rate goes at. Our clock picks. So what I did is I then tried to tune the HLS constraint, not the HLS constraint, the camera design constraints to try to be a little bit faster speed. I didn't have issues last time with it, but I took it from the 6.8 down to the 5.1, play around with the input delays. I need to go look at this a little bit better to understand how these delays affected and how these values were derived. But I try to get the clock to the placement route to place them a little bit closer together so we can do faster clock speeds. And so that's the second setting. The third setting was the exposure time. So before we were doing a 6,000 millisecond exposure time. 1,000 milliseconds, that doesn't make sense. This is like 2.8 milliseconds. I'm not sure what the metric for this exposure time is, but we reduced it by half. And when we did that, the color wasn't very good. So I went into Visual Studio and I went down to the analog gain. It was a 1/8 and I changed it to a 3/8. That 3/8 is the coarse grain. So we look at coarse gain. Is it? Where is it? Oh, I'll just go to the register value. What register value is this? Come on. Give me the register value. 3060. So if we go to 3060, right? What did I changed the coarse gain to a 3 right here. Okay. And what we're doing a 3 not on this table? Ugh. That might be a little bit of an issue. So what are we doing? We're doing a 3. So it might just be doing straight up this and not caring what this value is. We might just be doing a 12. So we just increase the gain of the coarse gain to a 3. Yeah. And yeah, we're doing pretty good so far. Where else is this? I wonder what the CB is. But yeah, we're looking at the coarse gain, and we changed it to a 3, and that gives a very good color here. And then we look right here. We have 60 frames per second, so we have the camera operating at 60 frames. Cool. Okay, so now let's try to get some HLS going. So first, let's go where we're going to insert the HLS. So I want to insert the HLS in the image IF system. So what we have here is we have these values are coming out here, right? And this is what I want to follow. And we want to intersect these values right here. Basically, do they even care about the other things? We have sync air. Do you use end of line? You don't use end of line. What about start of frame? Okay, you use start of frame, so we're gonna have to play around with those. Start of line. No. What about end of frame? So you do end of frame. What about sync word? Sync word. Okay, so it looks like you're just using air, start of frame, and end of frame in their state machine. So we'll have to make sure we change that around. Okay, so we're gonna do a we're gonna do a microblaze controlled HLS core in this situation. So we're gonna add a microblaze. We can probably keep it very simple. We want a UART. Yeah, let's just do our basic setup. Memory ECC, debug and UART. Yes, clocking wizard. We're gonna say none. We're just gonna use the PIX clock in this situation, so it's all on one clock. We'll say external ports. Yeah, I think that's all we need. We have the interrupt still. Okay. So now we're gonna add the HLS core. We're gonna go to IP catalog. We're gonna add a repository, and we're gonna add our IP repo right here. Oh, what board did I set this up for? Okay, so we need to go to project settings. Solution settings. Do not need this for a VU13P. I want this for the Opal Kelly board. Do you not have... it looks like I don't have it, so we're going to have to do the part manually. Okay, what's the part name? Here. XEM8320. XEAU. XEAU25P. It doesn't really matter. So the FFVB -2E. I like that. Okay, select that. Hit OK. We're gonna rerun synthesis. I don't know why my button is here. Let's go to this system. Where's this folder? So let's delete these. Okay, did we still get what we wanted? Yeah, it's really hard to read all the times when I decrease the monitor size. There we go. Now we're gonna export the RTL. There. That's the folder. Okay. Now we're going to extract this guy, rename him to basic adder. Now we go back to our IP repo and let's refresh the repository. Yay! Now we can add it to our design. Add IP to block design. Cool. See where that goes. You have to change that clock speed. Be 40 megahertz. I'll call it 0, enter, and then we'll call it clock. It's gonna be 40. Now all we need to do is make this external, make that external. Okay, now we have our HLS stream where the pixels can come in and the pixels can come out. Address editor. Simple adder. Interesting address to put the simple adder at. Go ahead. Put that address at the halfway mark. Happened. Did it work? Okay, cool. And for the other one, put that 4. 0, 0. Okay, cool. So now we're going to verify it, save it, look at the generate it, look at the template, and insert the template. IP libraries, block diagrams, synthesis, simulation. Okay, so now we're going to generate block diagram. So the goal here is to now try to connect this system and see how it works. While we're here, let us go look at the implementation of it. So I think we need to let's go ahead and just run implementation. Or we can go source. Okay, here. Value to add. That should be good. We'll let that complete the runs. So in this situation, we have an AXI input stream and AXI output stream. I'll show you in HLS how we've divided this up. So the here we go. So the data of the AXI stream is 40 pixels for 10-bit pixels, and the user is line valid, sync words, sync SOF, sync SOL, sync EOL, sync end of frame, and sync A. And we're going to send all this through the HLS and have it constantly run because we want the latency to be consistent to what the system was previously expecting, so that we don't upset what the system was originally thinking. See if we change this back so we can put a fit. Colors are still weird if we do that. Stretch, fit. See that back there? See. That's feedback from the gain. We don't see it so much with the big one. You see my looks actually pretty good on the other string. Playing around with settings a little bit. Stretch. That doesn't look good. That seems interesting. Got here. Maybe that's because we pushed the gain too high. Maybe we did, maybe we didn't. Okay, so this is still completing the runs. Hopefully we're okay if we click that. Okay, it looks like they're mostly done. Gotta say, this HLS has been a little bit more buggy than what I expect from previous runs. Block diagram, did we? It looks like we got what we wanted, so we go to synthesis. This project, Verilog. This project is Verilog, so whatever. Did it finish? I think it finished, so that's good. Okay, so we have a Verilog file, kind of wish for a VHDL, but that's fine. So we have this module we have to insert into ImageIF. So ImageIF, we have these systems right here. So let's go ahead and do a microblaze HLS filter, microblaze HLS instant 0, right? So we're gonna do that's where's the, they have the wrapper? I guess I could just create a wrapper. Hierarchy. Usually have a template you can see. Oh, do we have a template? Nope, we'll just have to create one then. So we go to hierarchy, go here, say create HTML wrapper. Sure. Use this as a template. So we'll open up this guy, and I copy how they've done the template down here. Yeah. So the clock, whatever clock this system's running on. The other clock. Yeah, so we're just going to connect the clock. Reset, we'll just reset high or low. Is this a high reset or a low reset? Properties. Active low. So we're going to set it as 1. Okay, so interesting that has a strobe on it. We're gonna say we are always ready to receive. This is gonna be open. Oh, I guess we're not even gonna specify that because we won't care. Where's the strobe play in this? Strobe. The only thing that's send in, everything else we can ignore. So we don't care about the strobe. We don't care about last or keep. Even valid. That's input stream. So it's always going to be valid. We don't care about it's ready. Doesn't really matter. I guess we could just tie those off. Start in the do not care section. Okay, so we need to create a 40-bit wire. We'll call it HLS input data, and we're going to do HLS input user, and do a bunch of these, and we're going to call it HLS. And where's those beautiful assignments? So we're going to do something like that. So we're gonna do what? HLS, what's it? Input. So we're gonna use the HLS input data, and assigned it the whole 40 bits of PIX data. I don't know, this one. I assume it's going high, low. So now we're going to do a user, and in our handy dandy lists, just going to walk down these ones. So the first one should be line valid, and then sync word, and then sync SOF, sync SOF, sync SOL, sync EOL, sync EOF, and then sync air. You know what? Let's go up here, and for these ones, call it HLS data. All those HLS. We can just replace everything afterwards. So those are the inputs. We don't care about that one. Or do we? How many bits wide is the strobe? Strobe, input strobe. I don't know why this would be a concern, but that should be all ones, if anything. There's 5 of them. So strobe, we're just gonna do 5B1, 1, 2, 3, 4, 5. Sure. HLS input strobe, and this we're just gonna call HLS data, and this is gonna be. Have to do something real quick about that. We'll do it. Oh, this is supposed to be 15. 15. 15. Do an output. Output user. Okay. And then we're just going to assign HLS. How did we do the line valid? The line valid. Didn't we do the line valid one? There's line valid. Oh, line valid is an output as well. Eesh. We want to intercept that earlier. So we'll do input valid. Okay, so we'll do a wire, right? Do HLS input valid. Intersect it that way. Line valid. Then we're going to assign HLS. We're going to assign line valid. It's going to be output user 15. Frame that way. And then assign HLS word. That's going to be sync word. It's going to be HLS. To do HLS output user 14 to 5. And then this is going to be what, 4? I have not done Verilog. That's the correct way to phrase these. We're going to assume it is. I am rusty on my Verilog. HLS start of frame, start of line, end of line, end of frame, and HLS air. This is going to be a 3, a 2, a 1, and a 0. Line them up. Okay. That should be good. Now, so what we want to do here is start at the top. We're not sending any of that stuff out. We're not. This is going to be HLS data. HLS data. Sync air is going to be HLS air. Picks, ready, HLS starter frame, HLS starter frame. I think that's everything. So let's see, sync underscore. They should all be there. Yep. Where we expect them. Sync air count. Okay, that's where they're defined. Yep. Okay, I think we are good. Since we've already done the microblades design, so let's go ahead and run synthesis to see if that works. And if this works, we'll see if we can add values to the camera while it's running. Then we're going to have to figure out the X, Y position, which shouldn't be too hard. The synthesis happy. But I don't know. Might not get very far if we're going this slow already. Thank you for watching. Hopefully, if you have any questions or figure out why you're watching this, what you're interested in, hopefully we can touch on it. Oh, we failed. This is good. How did we fail? Output. What did we call it up here? HLS. How far does it go? Plus. HLS. Okay, run synthesis. Hopefully that's good. Okay. Well, welcome to the stream. Right now we are trying to implement this block diagram. Hard to do this on such a small screen. This block diagram we want to stick between the video and the memory, the DDR memory buffer, so that we can see if hopefully we can be able to edit the raw video stream with HLS, and the whole infrastructure, the software, everything like that still supports it. So right now we've inserted this block diagram into image IF right between the camera phi and the output that right here is where we input it, between this and the output of this system. So hopefully that lines up and we're able to do our very simple HLS at the moment. So our very simple HLS, this simple adder, is just adding a static value to all the pixels. So basically just a fine gain across everything, where we can just visually add a gain to all the pixels, and hopefully we can white out the image. It is a integer, so we could put a negative value there as well. And see how that goes. So we'll try to make the image all white, and we'll try to make the image all black. It worked. Sweet. Yeah. That works. Let's generate the bit stream. Hopefully this doesn't take long, but it may. I wish FPGAs were faster. I really think it's important for people to have a demonstration of live development to understand the issues, how to resolve them, how to correct them, how to deal with unique errors or buggy software, how to use Xilinx's Vivado tool to the fullest, and when it's not useful, how to go down to the tickle or terminal level to be able to get what you want done. Unfortunately, it's slow. I can't show you the best examples, and I don't have time to necessarily run it all by myself, pick out the highlights and give it to you. So yeah, this isn't this is more of a hobby than anything else. So we get what we can get. Or as we through this, we can still. If we do this, then it. Still having these issues. I think the gain may be too high. We'll try off the other gain. Exit this real quick. We're just going to go to 400 right here. Let's try 30. That's what that is supposed to be. That's what the settings said. But I'm curious to what we get. Okay, it's better. We still got the colors in the background. But I think that's just an overflow, right? It has to be like an overflow in those colors. Yeah, the picture looks generally the same, so I don't think the fine grain did much in the situation. It does look like I have really lights in my background. Um, hmm. Wonder how easy. So we need to try some open source tools on this FPGA at some point. Unfortunately, we can't use the USB-C interface. Those ports, pins, protocol, HDL, API driver software is all obscured from the user. So that makes it a little bit difficult to understand what's happening on the board. But maybe we could try to figure out a simple system that works. We do have breakout boards that hopefully we can test in the future. I need to buy the pin or the pins and the jumper cables for this so I can get them installed and we can use them for fun things. But yeah. I guess we could start working on the next HLS core while we wait. Yeah, let's go ahead and work on the next HLS core. So we're gonna go a new project. It's okay. You never remember my location. Trying to get me annoyed. So we're gonna go here. We're gonna do a simple limits. Next, we'll add the files later. Let's get the right board. Family. Wait a minute, is it really under that? Subfamily Artix UltraScale Plus. We're gonna do the 2E. Oh, no. We want to go up. We want to do the age 6 speed grade 2. we want to 25. Doesn't probably matter in this tool. And we're doing a period of 25.5. That's what we are at right now, about 40 megahertz. So we're gonna hit finish. And our beautiful HLS core, let's copy over the source files. Headers. Really not using the test bench of them. Okay. Yeah, let's add those source files. Add source files. We'll limit source. And so let's go to H file real quick. Oh. We should probably do simple limits. Really didn't matter at all. Uint. We'll do red limit. We're gonna do well, I think it's gonna be green 1 limit, red limit, blue limit, green 2. Okay, oh, why does this software do this? It's getting annoying. Yeah, that's good, that's good. Green 1. Boop, 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 boop. Okay, we'll go green 2, red, oh, red, blue. Okay, so we have everything we need, and now we basically need to have an XY coordinate. So static AP uint uint 2 for this situation. Y column equals 0. Static AP uint A2 x row equals 0. Let me see. We go back to this guy, right? How long? I'd like to know how wide these start of lines are. Actually, it would be the end of line. Yeah. Technically, I think. So technically, that's only 1 clock cycle. What about the starter frame? What has the starter frame? Is this also 1 clock cycle? Yeah, it's 1 clock cycle. I don't even have to worry about the edge. So let's go back here. We're just going to say we don't need no. So if this happens, y column equals 0, x row equals 0. If so, so let's go back here real quick. Does that happen? Yeah, so that happens. So we're going to do else if user dot sync end of line equals 1. What we're going to do is we're going to say y column plus equals 1 and x row equals 0. Else if user.line valid is 1, x row plus equals 1. Okay, so now we need to determine what color it is. So go to here and we go to the viewpoint. We go to what, Bayer. Have a nice little diagram. So what they did is basically mod 2 red. Else if this is all happening with line is valid. Blue. Oh, well, in this situation we have 40 pixels, right? So 2 of one color, 2 of the other color. The column doesn't matter. All that matters is the row. And this is going to be green 1, red, green 1, red. So that's what it's going to look like when it's this pattern. And we don't even need, just need to know, oh, one. Did I screw up? Ugh, yeah, I screwed up. It's supposed to be X is column, Y is row. X, Y, Y, row, X column. And we care about Y row in this. I'm going to say Y row. That's how, and this is going to be blue, green 2, blue, green 2. Oh. How is this going? Okay, we're close. So if this is the case, what we're going to have to do is we're going to deal with the green ones first. So green 1 is P0, P1. And so we're going to say if pixels dot P0 is greater than green 1 limit, wait a minute, what did the simple adder do? Bring the data back. Did it actually bring the data back? Wait a minute. Oh, we did this at the end. Here we have that at the. I can just say pixels. Oh, we do. So we're gonna say P0 is going to equal green limit. And now we're going to do the second one as well. And we're going to do red, maybe P1, P3. P1, red. P3. Okay, now let's do blue. Blue. Blue limit. Green 2. Green 2. Okay, I think that's all we need for our HLS system. So yeah, let's go ahead and go to our project settings, synthesis, and select simple limit as our function and synthesize it and see what comes up. Solution. Vivado. Okay, we got this working, so we can play around with this. So yeah, what we're going to do is go to this other one. We need to go to this other one over here, and we need to close out this hardware manager so we can connect to the other one. So we'll go to our HLS01 file, no, hardware manager, auto connect, and go to the camera. Go back to this guy, and we're going to program it with our run. Hopefully this works. Do craziness. Whoa. We did something wrong. What's happening? Did we? I think we changed the color space a little bit. Nice colored headphones now. Yeah, it looks like we just changed the color space. Maybe the pixels need to be. Oh, we rotate the pixels in the assignment. Yeah, we rotated the pixels in the assignment. I know what we did. So here we go. We have changed the color, and it still works great at the 60 frames per second. Now let's go in and set it to white, even though it's the wrong colors. I don't really care. It's something we can fix later. Okay, so let's play around with these colors. XSDB, connect, targets, target 3. Target 3, memory read 08 1 2 3 4 1 2 1 0. Yes. Now we're going to do a memory write. Memory write, and what happens if you write XFF? Look at that, guys. Let's see if we can make it white. Can we make it white? So this is 10 pixels. So I think we can really only just do that, right? Is that how close we can get? 10 pixels. 10. I put a 2 there. Yeah, it's negative. We do a 3FF, like -1 E negative. So I think we need a 2. Let's do this 3, just a 2, 0, 0 that gets us our highest value. Okay, and now let's try our most negative value. Okay, let me see. Oh, it's probably rotating over. I forgot to set limits and bounds. Okay, so HLS works. We can play with our colors. Boom, we can make it really white. As close to white as possible. Yes. Beautiful. Okay. Figure our error messages here. Oh, we didn't do frame count. Oh, we have frame count. That's right. Probably keep the frame count. I'm just saying. Frame count, right? Okay. So frame count, and the issue is here we have the ordering wrong. It should be P3, P2, P1, P0. Okay, that should be good. We have default values. Can I assign? No, we won't worry about it right now. We'll start off at 0. So solution, active solution. Okay. There. Oh, X row. X column. The column at this point doesn't really matter. The row does. So solution, active solution. Let's go here, close out the hardware manager. File we're going to save as, we're going to call this HLS 001. So we can get this guy work. Ah, may not have time to get this guy to work, but we'll try. We'll try. Yeah, it's perfect. So we're gonna let's get this exported out real quick. Location, HLS repo, like folder, vendor AEW, library is gonna be Bayer, 0.0, display name simple, limit. So yeah, so we'll do this afterward. Simple limit. And we'll go to our IP repo. Finish implementation. Okay, so we're going to extract this to export. change that name. We're going to rename this to basic limit. HLS2. What we're going to do here is going to be really fun. We're going to connect them. So we're going to refresh your IP catalog real quick. Refresh. Boom, boom, boom. Simple limit. I guess we did simple limit instead of basic limit. I named them up left and right. So what we want to do, 3 megahertz. Address editor. What are we doing? You pick some really weird addresses, I gotta say. Now we're gonna disconnect this guy. Sometimes these ports do not like connect. 2 days. So we're going to have the adder and then the limiter. And we're going to pipeline these wonderful, wonderful cores. Now we're going to save this. And just like that, we are going to does it not invalidate these? Do I just need to like regenerate? Sure, we'll just regenerate these outputs apparently. Okay. Okay, I guess we will see how long it takes to get that set up and going. Go ahead and write 0. Yay. The colors are wrong. Oh, the colors are going to be wrong if I left it. Oh well, you guys don't really care about colors at the moment. We'll fix it in our last version or whatever. We'll pull something out. Okay. That really adding 1 does that. Adding 1 cannot be that bad. Oh, it's overflowing maybe? I think it's overflowing. The blue is overflowing to 0. That's why our lights. Let's generate bit string. If we zoom out, if we do stretch, yeah, we can turn on lights. Lights go crazy. So see our 2 lights. So the blue is overflowing in these lights. So if we set these to 0, it looks normal, but the blue is at the max, is at the ceiling, right? If we do 1. Wait. So if we do FF, oh, the blues come back and everything goes to 0. What we can do to our color space for funsies in real time. We could write software that just, increments slowly but surely. Really slow. 10, 20, 30, 40. Oh. 50, 80, 90. Whoa. There's where we get some fun effects. It looks like the green has overflowed and we have just the red remaining. A. maybe. Let's see. The blue's coming back with a vengeance. We got blue and red fighting now. Okay, back to Vivado. Let's see how it's running. Oh, we're already at the initial design phase. So we should be able to test this one out. We should be able to just murder one color. Yes. Or what should have been blue. Red. Okay, let's go check out if we know the memory map for it. So, not the memory map, the device tree, source. So we have different limits and carrying. Oh, we have a frame count. What was the frame count on this other one? Tell me your frame count. Simple adder, simple adder, basic adder. Patient miscellaneous drivers, software. Okay, let's read 18. That is a lot of frames we've gone through. Sheesh. Go through a lot of frames very fast. Okay. So this stream, I guess we're just going to wait out this implementation and then show off the limiting of the HLS course. I guess we could try to work on. So I guess we can try to do a little bit of pseudocode or talk through what we gotta do next. So next, we're gonna have to do we're gonna do a 3x3 kernel. We're gonna pull in some helper functions to get that done correctly. But we're going to need 4 different windows. One window for red, blue, green, and green 2. And then we're going to shift colors into them each cycle and do the calculations. We'll have to see. I'll like go. We'll have to do 2 kernel filters per, and then see how I'm able to operate correctly. There we go. Yes, it kind of works. Values, whatnot. But that's where we'll care about the X column. The X column is going to be, I guess it doesn't really. I mean, it's an index into our array. That's where that we're saving per each of these. We could try a simple mirror or something like that to play around with the. Maybe we'll try a mirror action. See if that works. Does that really work? I guess we'll just the top line. Maybe. Yeah, a mirror might be the next step to look at before we. So maybe we'll do. I'll do a mirror, and then we'll get close to the kernel, and we'll be able to show that next time. Might be to do that on Saturday. We'll see. Still working on this debug code. Well, I think it finished. So I did it. The make core is separate. Okay. Is there anything interesting to find out? Oh, yeah, let's do a test pattern, right? Messed with the colors too much. That's interesting. Well, shifting the colors, now we have well, let's see. Can we do Rob Bear? First. Do we should there. Um, uh, field thick. I guess we now have two greens instead of a blue, so the blue is just being completely ignored in this test. Oh, mono, and we're not going to see the color. Okay, image capture. Okay, we're in the play stage still. So we'll do a mirror filter next. I'll do a mirror filter as that'll be my assignment. I'll do a mirror filter as homework, and then start implementing the kernel. An example we can look at. I should have an example in my stream. So if we go up here, there should be a nice little folder called on the right here, stream. So if we look at this right here, the kernel, yeah. Look at this guy. Scrutinize this guy. We'll have to change that, but we have okay, we have a stream in, a stream out. Filter, red, green control. Yeah, we'll have to do this just like this. Grayscale it. RGB 3 line buffer size. Go. Okay, yeah. So do we have one that where's the we have one where we were playing around with those settings? Get it. Not one of these. Nope. Doesn't look like that. Repo. So what else? Not this one. Do CPP. Where did we do it somewhere else? See what that gets us. The current. This is our current place. It's not in our D drive. Yeah, I wonder if we have up the red. Yeah, I guess it would be in stream. Um, uh, Ready DVI2 sources, the block diagram. This is .vhd files. One that I wrote. Ugh. Fail the file. Yeah. Maybe I'll have to look at some old videos to see where those files were. That'd be fun looking at videos. Okay. I can do that over here real quick. I'm going to look at my old videos to see if I can figure out where that was. Oh, where's all this negative slack coming from? That doesn't seem right. Uh, Okay, I'm not sure where this negative slack is coming from, so we may have to reconvene, see what's the issue is with this terrible slack. Uh, yeah, what's this? Because, I mean, our clock is 40 megahertz. It should be operating on that. Did that's the clock it outputs. Clock we're operating on. So where's all this issue? We have a timing constraint wrong? Could be issue. Well, let's see what that issue is real quick and see if it's quick to solve. Yeah, you did nothing. Well, we can program it and see if it breaks it, but it didn't have. They're both running at 40 megahertz. Like we'd be able to do a lot in 40 megahertz. And it should be registering it between paths. Maybe I just need to create. Well, yeah, we'll go see what's failing. Um, I don't see why there'd be this jump in worst negative slack of a 3.334. It's ridiculous. Okay. Makes him wonder, did the other one fail as well? It's a really, really bad timing. Did we run this one with bad timing? Yeah, okay, it had the same timing issue. We must have changed something that broke everything. But it probably works fine. It's probably just something. So okay, so as soon as we get this up and going. Okay. Okay. Okay, I'm timing. So what is failing so drastic? That's nothing. Why'd clock die all of a sudden? It's a weird place to, fail as well. Why is this coming? Weird. Must be some weird, we changed it. Okay, weird. The system just doesn't like how the microblazes is now associated with it. Okay, let's go ahead and turn this off and reprogram the system. Program. Continuous. Okay, so the issue, this is the limiter. So if we go, we gotta go to the limits. So it's gonna be at 1, 0, 0, 0, and we can just, read 10 of them. Oh, that's not what I want. What's the register space we want to change? So let's do the reds. Red limit is at address 8. Well, we'll do green limit. So, 1, 2, and see something hard to see. 2, 0, 0. Okay, we got something. Let's try another channel. Yeah, we must have had something go on with that camera. What are the other addresses? We want to do 20 and 28. 2028. Yeah, we might have an issue with the timing. Or even our system. Oh, that's why we never assigned other values to it. We forgot to do an else. Oh yeah, P3 is either the limit or it's not the limit. So you have to balance it out. Okay, cool. I know why the HLS is failing. I think for the clock, our timing constraints. If we just go back here, let's go look at the report, the timing clock interaction report. If we do the clock interaction report, right? We can see that we've introduced a new clock, I think. Oh, we've introduced a new clock. This microblaze system that we probably can just say, nah, forget it. This is okay. It's okay. Well, good night. HLS core is working. We had a few bugs in our software. We can fix that in the second round. I'll go ahead and fix those next time. Get a mirror going, and then we can start working on the 3x3 kernel.